show, and for my CS 5526 project, I chose to do a time series analysis on the weather in Szeged, Hungary. So the data set we'll be working with is, as I mentioned in our title, is the weather in Szeged, Hungary. It takes weather data from 2006 through 2016, a decade over, and the interesting part is that it's not a daily data set, it's an hourly data. We'll go over the data set itself. So there's a total of 12 columns in the data set. We'll go through each one. The first one is the formatted date, which is the most important part of a time series data. So the second column is summary. The third column is the precipitation type. So it'll either tell us if it's rain or snow that's falling down. The fourth column, which is the most important column and is the independent variable, is the temperature column in Celsius. The fifth column is the apparent temperature. Next column is humidity. The seventh column is the wind speed in kilometers per hour. The eighth column is wind bearing in degrees. Ninth column is visibility, is how far out you can look, which is also in kilometers. The 10th column is called loud cover. The 11th column is pressure with the units of millibars, so it measures the atmospheric pressure. And the last column is the daily summary. First need to look into the missing values. The only parts that had missing values were the precipitation types. Through my analysis, I realized that precipitation type was not as significant in predicting the temperature, so I removed it. So therefore I didn't have to deal with any forward filling, back filling, or taking the average of how many, or taking the mean or mode of what value appeared the most. So the next thing we'll be looking at is the dependent variable, as I mentioned earlier, is the temperature versus time. You can see here, as you would expect from a weather data set, that it is very seasonal. So you can see how it goes up and down. The temperature ranges around -15 to 40 Celsius. There doesn't seem to be any significant outliers except for the 2012 winter, but that could also be just explained as an exceptionally cold winter. So you can see here it starts at 1, then slowly, and the PACF of the dependent variable, it starts at 1, and then on the second lag it drastically drops. The most important part of this is figuring out which features I mentioned earlier had high correlation to each other. So as we chose the independent variable to be the temperature, I had to eliminate the features that were highly correlated to temperature. And as you can see here, the apparent temperature, which I mentioned earlier, is a combination of humidity and the temperature, has a correlation value of 0.99. So essentially they're both the same things. So with that, I removed the apparent temperature, split the data set, and as you can see for a time series data set, I took the first 80%, so 2006 up to 2014, and then I took 2014 data up to the very end 2016 as my test data set. I also did an OLS regression result to see which other features I had to get rid of. You can see here that the apparent temperature has a very large coefficient. The other features, however, don't have that high coefficients. I also performed a VIF for each feature, and this also supports the OLS regression and the correlation matrix. So you can see here the apparent temperature has a value of 128, which is significantly higher than the other features. One thing is the loud feature. So I took a look at the loud feature by doing df describe, and I noticed that all the left cover values were 0. It wouldn't make a big difference on predicting the temperature, so I also got rid of the allow feature as well. So next up, you will check the stationarity. So in order to check the stationarity, I performed the ADF test and the KPSS test. So if you see on the left, I did the ADF and these are the results. The p-value is surprisingly 0, but so I looked at the KPSS test and the p-value is also significantly low. It's lower than the threshold point 0.05. So with that, I looked at the rolling mean of temperature versus time. Doing the rolling mean does not change much. You can see the variance here over the 30 days, and it seems to be peaking more than the original data. So I performed differencing on the original data, and this is what I got for a rolling mean. It is almost constant, almost at 0. I also did it for the variance as well. And now, in comparison to how it was way above the variance for the original data, now the original data seems to be less than, no, my bad. The variance seems to be less than the original data now. With that, I went ahead and did some time series decomposition. You can see here that just like you would expect, the data itself is very seasonal. It's almost a full bar, as you can see, and it also makes sense because it's a weather data set. And you can see the trend, there's a trend as well that goes along a line with the temperature. And I also performed differencing on this, and it aligns with what we got from the previous slides, and it's still trendy and it's still seasonal. So with that, I went ahead and did the Holt-Winters method. So for the Holt-Winters method, it did not perform as I would thought it would have. The predicted values is strangely off. It seems to be between 10 degrees and 15 degrees, more as it kind of took the average of the temperatures. But we shouldn't jump into conclusion just by looking at the Holt-Winters method. So I wanted to do a differencing of the Holt-Winters method, and I got similar results to when I didn't do differencing. It was just between a smaller range. But like I said earlier, I didn't want to jump to conclusions thinking that this was a bad method to use. I assume that this method may not be the right kind of method for this kind of data set. So with that, I went over to the base models. So before I did anything for these base models, I calculated RMSE for each method. So the RMSE for the average method, naive method, simple exponential smoothing, Holt-Winters linear method, and the Holt-Winters additive method all seem to have similar numbers of 8. But for the drift method, it was significantly higher, not as twice as much, but a lot more than the other methods. So when I was doing my project, I took a cautious look at the drift method. So we'll go over the average. So for the average smoothing, as you would expect, you can see that there's just one straight line, which makes sense because it's taking the average, and every year weather data shouldn't drastically change the range itself. So what I'm saying is, let's say for winters, there should be a range, like it can't hit 40 Celsius and then go down to 20, like -20. it should be around the range of -20 and 10, so it goes up and down from there. And then for the summers, it would be 20 between 40, and it goes up and down there. And then once you take the average between the two, you would get something similar like this. So nothing surprising here, but you can clearly tell that it's not a good model to use for a weather data set. Next, we have the naive method. So this was also not surprising in the way that it almost aligned with the test data set. However, this also makes sense because the way naive smoothing works is you take the previous value, and like I said earlier, weather data is not something that drastically changes overnight. In certain situations, it could change from, let's say, 30 Celsius, and then the next day it could drop to a 15 or 10, but that rarely happens. You kind of have a trend when it comes to weather data, and this model explains that perfectly. So it takes the previous data, in this case it took the previous day, and then it made a prediction out of it. So you can see the glimpses of the test data on the prediction, and it worked the way it should work. Next model we have is the drift method. So for this one, it was kind of surprising because I was not expecting a straight line just like the average smoothing. In a way, it seems very similar to the average smoothing, even though it's calculated in a different way. So by looking at this, I concluded that the drift smoothing was not an optimal model to use for weather databases. Next, we have the simple exponential smoothing. So here, I took in different values of alpha and calculated the RMSE along with each alpha value. So you can see here that when alpha is 0.5, the RMSE is the highest, but it seems that it made the best predictions out of every alpha value. So you see that it makes slightly higher predictions than the test data, which isn't the best because it seems to be overvaluing what it based on the train data. So this wasn't the best ideal model, but it was it was one of the better ones compared to the average and drift methods. So next up we have the Holtz with linear smoothing. I also set up different alpha and beta values along with the RMSE, and you can see how the larger alpha values tend to have a larger RMSE value. And for this one, it seems like the one with the highest alpha value and beta value predicted closely to the test set. But as similar to the simple exponential smoothing, it seemed to be a little bit overvaluing what the train data has fed them. So as of now, this is not the best model either. So the last base model we're going to look at is Holtz exponential smoothing. So here we have an alpha values of 0.99, and just like the other ones, it has RMSE beta values. And similar to the other ones, it's overvaluing. It makes higher predictions on the temperature as the other ones. So from what I got from these base models is that they are not the best, but they are passable as of now before we go into the other models. So with that, I went on to the next model, which is the multiple linear regression model. And for this one, I performed the OLS, obviously, and then I did the F-test on the different features that we have. And you can see here that humidity has a very high negative coefficient with temperature. And the other ones like wind speed, wind bearing, visibility, pressure, they don't really seem to affect as much as the humidity feature. So doing the t-test, we get these different values. So humidity is significantly higher than the other ones. It has a negative 227, and the wind speed has a negative 660, which is also very high absolute value wise, but not as high as the humidity. And then we have wind bearing 15, visibility -8, pressure and -8. And I also performed the AIC, BIC, RMSC on both train set and the test set, calculated the R squared, got the Q value, P value, I got the residual variance and the residual means. I also got the ACF of the residuals. You can see there's a decreasing trend as the lags increase. So with that, I looked into the different models that was stated, and the one I'll be introducing the slides is the ARMA one. So I plotted the ACF and PACF of the ARMA, and you can see that the ACF starts at 1, then slowly makes its way down, but it never hits the confidence interval, nor does it drop down below 0. However, you can see in the PACF that around order 1, it drastically drops and goes below negative. So between 1 and 2. So from this, I came up with the orders of 1, 0, and then performed the 0 pole cancellation and then plotted the residuals. So the 0 pole cancellation, you can see the pole got canceled by the 0, and the residuals, it looks very similar to when the temperature got differenced. Next up, we have the SARIMA model. So the SARIMA model, what I actually did was I went through all the different types of the different orders that were possible, and then it took me a while, in fact 3,000 seconds, and I came up with the best model that ARIMA 101 211 was the best fitting. So I took that and I made a forecast out of this, and then unfortunately it did not perform as well as I wanted it to. I had to look into why this SARIMA model did not perform as well as it should be. I assumed that the parameters I obtained were wrong, and I have tried to make multiple attempts to make it better, but this was the final SARIMA model that I was able to achieve. So I also did the Levenberg-Marquardt algorithm for the ARMA model, and these are the results that I got out of it. So the estimated coefficient was 0.9685. I got the estimated covariance matrix, the variance of error. I got the confidence interval for each parameter, for each feature, and then the p-value. And lastly, I implemented the deep learning model. So if you look at the deep learning model here, you can see that the prediction is extremely good, and it's kind of similar to the naive method that was implemented. So with that, unfortunately the SARIMA model did not perform as well as I wanted to, so I chose the deep learning model as my final model. So in summary, Um, it would have been better if I was able to spend more time on finding the optimal parameters, coefficients for each of the models. I already spent significant time on the Serima model, and it was difficult to find the perfect coefficient parameters just because the dataset was extremely large, and this also goes in line with my third bullet, which had I also had hardware limitations. It would have been a lot better if I knew how to take advantage of a cloud service that had more computing power. I unfortunately did not have enough time to familiarize myself with that to implement it into my final project. Um, the next thing I wanted to mention is that the deep learning methods, we were only able to go over one deep learning method, and the one deep learning method we went over actually performed the best for me. So I got to thinking that other deep learning methods could actually perform better than the one in terms of making forecasts for this weather data set. So going into looking into different deep learning methods would be future work for this project. And the one thing, a personal thing that I did lack was working with real data sets, and because I have little to no experience working with real data sets, I did not expect it to be this difficult to come up with a good model to make predictions and forecasts. And with that, that is my presentation. Thank you.